Good evening, everyone. Welcome back to the Astro Imaging channel. Tonight we have George Hilios, who's going to present his, hi George, you see him there on the screen, present his Hocus Focus utility for Nina. And I haven't used it personally, but I've heard a lot of really good things about it. Hold on, let me just skip this. And I think it's going to be a very interesting presentation. And of course, you out there, put your questions for George on the chat and we will relay them over. But before we do that, as usual, I'm going to share my screen. I'm going to share my screen, entire screen. Is it come up yet? Our calendar come up? It should come up. Not yet. No, I don't see it.
I'm not seeing it either.
Well, let's do it this way. In order to share the screen, you got to click on the window. There we go. It should come up now.
Got it.
So we got George tonight. Next week, Ron Brecher is going to talk about 4 meters and counting. I assume he's going to talk about a 4-meter scope. And that should be interesting. And you see, we have 3 open dates for the following 3 weeks. And of course, anyone out there that has a topic they'd like to talk about, you don't need to be a professional presenter. You just have to be willing to come on and let us know that you have a subject that probably other astrophotographers will be interested in. And all you need to do is go on to our site, and somewhere in there, there is the contact form, this little guy right here. And put in your name, other information, and tell us, hey, we'd like to present. And we would, someone will contact you and you'll be on the show. So let me stop sharing. Stop sharing. Stop sharing. I'm a little bit slow on the trigger tonight, but we're back. And if we don't have anything else, I'm going to turn the show over to George and you can tell us all about Hocus Focus.
Thank you, Eric. Thank you all for inviting me. I'm excited to talk to you today. So it's just a little about myself. My name is George Hilios. I've been a long-time contributor to Nina. Hopefully many of you have used it or at least heard of it, but it is an open source astro imaging software application. And sort of one of the things that we're trying to do with it is democratize access to really world first class tools for astro imaging. And so, I've been a contributor for several years. Some of my first contributions included adding dome support. When I had a next dome, I've since upgraded to a slightly nicer observatory. And, things continue working there, thankfully. But what I'm going to be discussing with you today is one of the plugins I've created called Hocus Focus. And so, rewinding back a couple years ago, Stefan and I were sort of batting around some ideas about how do we make it so that Nina can get new functionality that is very sort of niche for really like specific use cases without really like muddying up the core code base. Thinking of like, hey, I want this new functionality. Do I have to do a big application release for everyone to get it updated? Right. So in sort of software parlance, you can have multiple release channels. And that was sort of where the plugin system was born. One of the first plugins was actually like Hocus Focus, because we were figuring out how to structure the plugin system to allow for, say, something as big as a custom autofocus engine. And the reason why I wanted to do this was because, a lot of the autofocusing algorithms out there were very sort of opaque. Right? Like you just hit go and you count on it to give you precise focus. And I really wanted to have this sort of iterative scientific approach to achieving really perfect focus, and to do so in a way that is sort of specific to everyone's own optical setup. So really the only way to really explain this, the best way, is to show you some live demos. So I'm just going to open up Nina. We're going to go and do this sort of by the seat of our pants a bit. I know that should strike fear in the hearts of any programmers out there, but you know, I've used this a lot, so I'm confident it'll work. And also, if you have any questions, please raise it in the channel. You know, I would appreciate this being sort of interactive. So let me share my screen real quick. Let's have... All right. Hopefully for many of you, this is a familiar screen. This is the Nina main image tab page. And so what you're seeing here is the autofocus tab. It's blank. We've not really done an autofocus before. But the first tool in our workbench that I really want to show you is this thing called a simulator camera. And I'm going to build up to what an autofocus looks like. So here's where we're going to start. With the simulator camera, you can open up an image. Let's grab an image here. Now, ignoring the paths for a moment, but this simulated camera, I've now opened an image. I'm connecting the camera, going to our imaging tab, and I'm just going to take a single exposure. It's not bared. Let me disconnect and reconnect it. There we go. Okay, so what we see here is an image from a user that shared their images with me to debug some autofocus. If we zoom in, you can see the star annotator at work. You see a box, you see a number next to it, and under these star annotation options, you can sort of see what it's doing. It's drawing a box around every detected star. The property it's showing is the half flux radius. And one of the things that should stand out to you when you're looking at it is this kind of sucks, right? Which would not be obvious if you didn't have an annotator to look at it, right? This box is clearly too small. This one is as well. And look, you're seeing these 8s and these 3s and these 5s. The numbers are all over the place, right? And so if you did an autofocus routine with this setup, it might look fine, but the data are bad. And if the data are bad, your focus is not going to be really great, right? So the first tool to really be mindful of is the annotator. You run it through your star detection. You actually look at the stars, and some of these actually look fine. All right, and I'm going to walk you through in a little bit how you go about tuning this, but I sort of want to build up our workbench. So the first tool I mentioned here is the star annotator. It literally can put in an image that you've previously taken and view what your current star detection settings would do. The next tool is sort of a cool little feature here. You can loop. You're going to take pictures, but see, it's the same image. The camera just has a single image loaded into it. So what happens here is if I go into my star detection options and I go to change a setting. Now, I know what setting I want to change, but I'll explain what this is later. If I change one of these, it's still taking these looping exposures. So the settings, the star routine, the star detection routine sort of automatically picks up the next setting on the next looping exposure. So what this does is give you a feedback loop. As I change my settings, I can see how my star detection improves or gets better. The other tool you want to be mindful of here is the star detection results page. This provides some useful statistics for you, sort of like the average half flux radius. This is a measure of dispersion, standard deviation. This one is actually the median absolute deviation, similar spiritually to standard deviation. But you know, generally, if this is less than 1/10 of your half flux radius, there's likely that your star detector needs some tuning. So that's one element here. And the next tool we're going to build up to is in the plugin page. under Hocus Focus, there's this little button here, Save, and you can put a path. Now, I'm not going to click Save here, but you're going to view the output of what happens, right? So Save is turned on. You give it a path, and you run an autofocus routine. What's going to happen is you can go to this autofocus page, click Reprocess Saved Run, and here it is. There's this pop-up. You can pick your page. Let me go to some of the data I squirreled away for this. Go to Attempt. You load it, and what it's going to do is it's going to replay that autofocus that you previously did with whatever your current settings are, right? So you can say, all right, my autofocus wasn't great, but I saved it. It's daytime now. I'm going to go tune my star detector without, having to deal with cold hands or lose any precious imaging time. So, in the spirit of having something iterative and scientific, the idea here is that we have these parameters, you can tune them, and you can view the changes live, right? So you don't have to wait to do a full autofocus run to see the impact of your changes. And ultimately, those are the main tools here, right? I'm going to go into a little bit more detail about what this star detector is doing. But if you have any questions, please sort of ask away and interrupt as I go, because I know this is a lot of, this can be some dense material. All right. So one of the tabs here, I want to go into a little bit of details about is like, what happens if your star detection, if your autofocus routine gives you some like bad output? How do you go about it? How do you debug? I picked an example here that I know has some pretty bad behavior on the default setting. So I'm switching back out of the advanced mode, going back to our default settings, and I'm going to run this exact same autofocus routine again. And check out how terrible that looks. I'm actually going to make it even worse. I'm going to go into my plugin settings, and I'm going to turn off a setting that I added in the last year. I'm going to run it a third time. So you see we're at about 4307 for an optimal position. Let's run it again. And here this is 4382. So we have what looks like a slightly different slope on the right-hand side of that curve. We have something steep on the left hand, and then we have a hyperbola here that is trying to sort of split the difference between the two of them. Not really getting it. Like, you can just visually tell this is not really a good output. And yet, a lot of the star detection, a lot of the autofocus routines we're doing, these are real curves, right? And if without sort of visualizing the data and seeing that the curve actually doesn't fit the points supremely well, like that sort of begs the need for a different setup, different way of fitting our curve. So let me go into the two things that I just changed. The first one is related to this point right here. This point clearly is pretty far off, right? And the way I would go about debugging this is loading up that image in the simulator, finding this thing all the way out. This is a focuser position is roughly 5,000. So let's go load that one up. So go into the simulator camera. I'm going to load up under attempt 01. Actually, that was the one I had loaded. There we go. I'm there already. So when I go into image and take an exposure, I'm going to turn looping off. Let's see what we're looking at. So I had mentioned earlier that we had some bad detection results, right? See, this is an example of a star that was too, the bounding box doesn't really fit it very well. Now, 9 times out of 10, if you're getting a result like this, it's because the detector has a hard time with your setup figuring out when the star ends and when the background begins, right? I mean, this is really heavily stretched, so you could kind of see visually, but the detector needs a little bit of help. And so the most common setting to change here is really just the sensitivity of the detector. And so to change that, you go into this advanced mode, and there's this brightness sensitivity. And to make it less sensitive, you increase the value. And so let's put 30. 30 is one of the values that tends to work for people when this happens to them. If we take another exposure, look, what happens here is it says, now I don't have confidence this is a star anymore, and it's more likely to weed them out. And so what we're left with here is something that fits better, right? It's still not perfect, but we've gone closer in the direction of something that looks reasonable. You know, you can zoom in with your scroll wheel on your mouse and look at the different stars. You know, that one still doesn't look great, but if you wanted to go even further, you could say, do what happens if I set 40. In this case, even increasing even further is not really having much of a difference. So we say, all right, let's just leave it at 30. And then see, the next step is what happens if I run the autofocus through it with these settings. Again, the exact same data, right? And so we have something that looks better, right? It's closer to what we were looking for. And what you also see here are these bars around each of these measurements. These are the error bars. So the more dispersion you see in the measurements across your field of view, the larger these bars are going to be. That's one thing. Now, this isn't perfect. You know, if I were looking at this, I would tune some other settings further, but for the sake of the demo, we're just going to sort of stop at that one property. But the other thing that you should notice here is that, look, this, again, the slope of this looks different than the slope of this on the left side. And so when observing that, not just my optical setup, but a lot of the people I was getting data from, they showed me that their optical systems had this type of setup where the slope on one side is flatter than the slope on the other. And I spent weeks changing the algorithm, trying to figure out, like, why is my detector doing the wrong thing? Because all of what I had heard is just use a hyperbola, right? This is what the literature says. But let me share with you a slide that I presented at NEAIC. I presented this about a year or so ago. There is
George, while you're sitting,
that I'd like to share. This one right here.
George, can you hear me?
I can hear you, Alex. What's
okay. John wants to know if we're on the generic autofocus or are we in Hocus Focus?
This is a Hocus Focus.
Okay. I think that answers John's question.
Okay.
Thank you.
George, I have one more comment.
Sure.
Congratulations. Data is plural. And only a technical person is going to know that. I'm sorry, you said that right away. A scientist prejudice. Data is plural. Sorry, go ahead.
Okay, thank you. So I was mentioning that I got a little lost in the algorithm for a while, convinced I had done something wrong because everything I had read had said that this should fit a hyperbola shape. But then I looked at the data, like, a picture tells 1,000 words. And these images here, exact same star at this point of the focus routine and this point of the focus routine, these are what the stars looked like, right? And what turned out is when in focus, you had, for this optical setup, this sort of bright halo around the outside, and on out focus, it was very sort of flat, like a matte paint finish, which meant the measurements are going to be different. And so since the measurements are different on in focus and out focus for this type of optical setup, we need a different type of curve. And what I ended up doing is implementing this sort of uneven hyperbolic fit. And it's actually on by default, so I turned it off just to sort of make the point. But it wasn't in the original version I had released. And so when it's like this beforehand and running it through the algorithm one last time, we're going to get something that fits even better. And here we are, right? So we have the slope on the right-hand side respected, as is the left, and we have a better measurement of where we believe the optimal focus area is. And, You know, going back to the data argument I was making earlier, that this is the type of thing that I've seen in no literature, right? That this is how often, and maybe there are some write-ups here, but the point is I wasn't able to observe this without having a tool that could let you replay and do it in a way where people could send me their data and run it through. So we've been using the contributions of all the users of Nina to make this focuser better and better over time. And these are just like sort of a taste of some of the improvements that have gone into it. Another example of a thing that leads to like different behaviors is like what happens if you have something like a Schmidt-Cassegrain telescope, right? Let me pull back this slide again. Now I don't own one, but several of our users do. And what they showed me is that their stars, I don't think I have an image of one of them here, but you have a donut shape, right? Where there's literally no, there's black space in the middle, which is from the secondary obstruction. And you really, really see it when you're far in or far out of focus. And what happened is that sort of wreaked a bit of havoc in my star detection algorithm, because one of the settings, and I'm going to point you to it right here, is this thing called max distortion, right? And the idea is if the star detector puts a box around something it thinks is a star, it's got to do a bit of an analysis to figure out what is the likelihood this actually is a star or just a random box, right? And so when we're back at the image, these let's turn on this annotator again. What happened? Oh, let's take, here we go. So this is an example of a star that it accepted, and this is an example of one that it did not, right? So in order to avoid getting rejected, one of the things that it does is counts the number of pixels that are below the noise level, black, right? And if more than half of them are black, you know, background, then it discards it. It says this could just be nebulosity. It could be something else entirely. But what we found is that when you have that secondary obstruction, it skewed this metric. And so people with Schmidt-Cassegrains, depending on their setup, they found that they would have to reduce this to say like 0.4 or 0.3. So 9 times out of 10, when people are modifying these properties, they're modifying sensitivity, or if they have a Schmidt-Cassegrain or anything with a secondary, they're modifying distortion. But by and large, the rest of the stuff has sort of stood the test of time. They don't really get modified all that much. But when people come into the Nina Discord and they ask for help, like, hey, my autofocus isn't great, the first question I ask them is, have you loaded your image in the annotator? And this is what I mean by load the images at the edges and at the bottom of focus, and just see how well the detector is working with your current setup. So I wanted to pause to see if there are any questions.
Could we hang for a second here? Now, this looks more like a hyperbola. Perva wants to know, is mathematically, is this still a hyperbola? Is it a rotated hyperbola? I would ask the question is to say, if I remember what a hyperbola looks like, is that what my graph is supposed to look like?
Yeah, it's a good question. I could not figure out the mathematics for a rotated hyperbola for some time. Let me pull up a slide here. This is what the mathematics look like for a hyperbola, right over here. Now, I didn't, at the time I did this presentation, I had a different approach to calculating a rotated hyperbola. But what I ended up doing is adding a 5th parameter that blends 2 hyperbolas together at the bottom. And so it goes from being a 4-parameter function to a 5-parameter function and gives us different slopes on the outside and on the inside. So instead of actually rotating it, what it does is blends two hyperbolas together. And only one of the parameters needs to change to do that.
Okay. While we were talking here, John at Astro asks something that I bet you'll be getting to eventually. Why Hocus Focus over the standard Nina focuser?
I skipped that detail. Thank you for asking. So the previous focus routine was implemented sort of in a throw darts at the wall and see what sticks way, right? There were a lot of magic numbers in there, right? Things like if this value is less than 0.4, then it's highly likely it's a star. There were blurs and Gaussian blurs, etc. So there's a lot of matrix operations on the image that were found to do a reasonable job at determining if something was a star. But what we were observing is that there were a lot of setups that didn't work well on. And when it didn't work well, we couldn't explain why, right? We're just like, oh, well, I think we need a different algorithm to figure this out. So the point of Hocus Focus was to go back to first principles and do like standard image analysis on the star field in an effort to extract the structure. So we're doing things like wavelets, doing things like blurs and subtractions to find things above a noise level. Honestly, like a lot of operations that you should be familiar with if you're using tools like PixInsight, etc. So the reason,
George,
sorry, go ahead, Eric.
I have another question. So will Nina use something like Focus Max as its focus utility, or is that completely outside?
It's completely outside, right? So part of the issue with using something fully external is that you have to give the images to that external utility. And doing those like write to disk, give a file, like those types of operations tend to make autofocus routines take longer. So the point here was to have something fully in memory, but I don't even know if you can do Focus Max.
Well, does the Focus Max just go with the slope of one side of the curve in order to get its focus position, which according to what you showed us, that would be the wrong way to do it. You get a V curve in Focus Max, and then you get the slope of one of the sides of a hyperbola, and then you do 2 points and you extrapolate down to focus, assuming both sides are the same.
Mm-hmm.
So what you're saying is that's probably not the best way to do it.
That is what the data have told me, right? That we would need 2 different slopes on most setups to do that correctly. That's right.
Okay, thank you.
And that clears the questions for right now.
All right. So once autofocus was sort of in place, this stabilized. We've gotten a lot of mileage out of it. I had a few interesting conversations on cloudy nights with a fellow named Chris White. And I'm going to pull up a slide here just to show you. This thing ended up being, I think, 114 pages long. Now, not light reading by any means. But for those of you that saw this tilt discussion, a conversation in Cloudy Nights, the idea was like some ideas presented by Chris White and others, like how could we systematically measure tilt in an effort to improve our images? And an interesting debate sort of ensued, right? So Chris was advocating for this approach where you would take an image, you would do sort of autofocus in the 4 corners, determine the points of focus, and from there, he put it in Excel and did this all manually, right? And over time, Hans, who was working on ASTAP, was making improvements to ASTAP to sort of systematize that process. And I had a few conversations with Chris and Frank Freestar8n, who is the author of MetaGuide, about like what is an alternative approach to the 4 corners that could be like rooted completely in science. And Frank's argument at the time was you know, when you are measuring a star field, right? Like the definition of tilt, right? The definition of back focus is that when you have tilt and when you have back focus, the different parts of your sensor come into focus at different times, right? So imagine you had no back focus, you had no tilt. At the exact moment you enter optimal focus, all of your stars in the entire field are perfect, right? But, you know, that's not the reality a vast majority of us face. You know, when you have back focus, maybe your center comes into focus at a different time of your corners. And when you're tilted, you know, one of your corners might get into focus before the other and vice versa. And so that was where Chris White's idea was to measure, you know, break apart a grid for your sensor, do an autofocus routine on those corners in the middle, and then you could do some analysis to figure out, you know, do you have tilt? Do you have back focus issues? And then, you know, how do you go from there? And one of the downsides to that approach, from Frank's point of view, was that you're taking an average of that entire region, right? Why not use every single star in your field? And he said, well, if you do an autofocus on every individual star in the field, you could calculate the curve, that paraboloid, that three-dimensional parabola of your focus, and then from that derive your tilt. And you know, sort of crickets landed in the background because no one really wanted to implement that. But you know, that sort of tickled my my curiosity, and I wanted to say, could I use Hocus Focus to do both of those approaches and sort of battle test them against each other and see, does one actually yield better results? And that's sort of where the Aberration Inspector was born. So for those of you that haven't heard of it, there's this tab in autofocus and Hocus Focus called the Aberration Inspector. And the purpose of it is to measure a back focus errors and tilt errors in your imaging train by using an autofocus routine, right? And so it works exactly the way I described. It takes an image, it does an autofocus routine, and it does autofocus curves for every single star in the field. And you can also feed it saved autofocus routines outputs in the exact same way we do for a regular autofocus. So let's give it one. Let's actually give it that one we did already. This I like a different one. Let's do standard example here. And so here, let's let this run for a bit. I know this is using saved data, but normally if you go to run autofocus, you could do this live. Great. Okay, so what you're seeing here is a three-dimensional representation of what that curve looks like for the imaging train. What you see here is that at the corners, these two corners, you come into focus at a far different point than the center and the other corners. So we see a combination of tilt and back focus problems in this setup right here. And going down here gives a few different views into that data. Here's sort of a plane type representation of what that tilt looks like. And here's some numbers behind it in terms of measurements. How tilted is this imaging train? What does the curvature look like? Now, the numbers I have in here include things like the focal length, the pixel size, the pixel scale of your setup. This is someone else's data. So the information in my Nina instance don't match the data. So some of these numbers are off. But conceptually, I hope you're sort of following along here, that when you're looking at the output of Aberration Inspector, it's telling you you have this amount of tilt and you have this amount of back focus error. Right? And so this is telling you, because there's a lot of curvature, you should adjust your whole imaging train up or down. And then this is saying, because the corners come into focus at different points, you should, you know, get a tilt corrector They have a couple of different ones on the market, and do so accordingly. And then this becomes an iterative process. You make an adjustment, you run it again, and then ideally you see it start converging onto that flat, perfectly back focus adjusted setup. And the other thing I want to show you is I mentioned about battle testing the approaches against each other. Fortunately, what we can do is if you turn this off, you get exactly the analysis that Chris White did in his thread. So these are curves for the center, top left, top right, bottom left, bottom right, etc. And if the setup were perfect, all 5 curves would sort of converge. And what this chart is telling you is that both approaches actually agree with each other. But we are able to distinguish between curvature and and tilt in a bit more detail with that that point-based model, right? So I'm not able to say like draw a 3-dimensional curve here to visualize it, but we can see the degree of tilt and provide some estimates for that. So I'm going to pause here real quick if anyone has any questions.
Hang on, and by the way, I don't know if we've reminded you that we're on a delay here, and when you say I'm going to pause, we have to reach up and unmute ourselves, and so it may take a. We're here, we just have to unmute ourselves. Isaac wants to know how you set the default settings. How were those default settings determined? Under what conditions do the defaults work well?
Yeah, so let me switch into the star detector options here. So when early in the days of Hocus Focus, I was figuring out what the parameters needed to be, and this is what the page looked like. No one wants to work with this page. I don't want to work with this page either, right? Like there are too many settings. And I didn't really know what values to put for these without data, right? And so I got autofocus runs provided by dozens of Nina users who were sharing their data freely with me to find what values of these work most of the time. And what I found is they fell into certain camps, right? So let's drop into the simple mode. The simple mode here is just a nice little like wrapper around the more complicated settings, right? I found that for users of newer sensors that have very low noise, they wanted to have there's a setting that indicates this is a low noise sensor, and we got better results by modifying it based on the generation of your sensor. So if you have one of those modern QHY like 600s, then you would want to have something that the noise level is low or typical. And if you have something like one of the older AA 1600s, which I used to have, right, we wanted to set that to something higher. Like those were just noisier sensors. The next 2 settings were really around being a long focal length scope or a very wide field one, because that indicates how big the stars are. This uses wavelets. And so there's how many levels are used in the star detection routine, right? And so generally, most people fit in the typical, but if you're using, again, a Schmidt-Cassegrain, something that has a very high focal length, like 1500 above, you typically want to go long focal length. And if you're using a camera wide field, then we shrink it below the regular. This one's not as commonly used, but it's there for completeness. And then the last one is there are some users that like getting very big curves that go out to like 10 to 15 HFR on the ends. And if you're doing a very, very wide range, there need to be more levels in the structures. And so focus range of wide range is there for them. So between those 3 settings, like that covers, I would say like 95+% of the cases. And I figured that out by looking at people's data. Once you pick your setup though, say like long focal length and low noise, once you go into the advanced mode, those are the settings for the basic ones you set already, and you could do further adjustments from there. But a vast majority of the time, people only end up modifying sensitivity.
Okay, thank you on behalf of Isaac. And that takes care of it. George, you okay?
Yeah. Oh, sorry.
Yeah. I'm just saying. It looks like we've got all the questions out of the way now.
Okay.
Okay.
Excellent. So, I mean, that's essentially the entirety of Hocus Focus here, right? So when I was building the Aberration Inspector, I was speaking to a fellow named Keith who developed the oh, I'm drawing a blank on the tilt adjusted octopi. There you go. And he wasn't convinced that it would be easy to use a tilt adjuster like the one he wanted to build with 4 points, because there just weren't really any good tools on the market for doing this type of analysis. And this was in like the middle of having that mega cloudy nights thread. So I convinced him to build a device, send it to me at cost, and that I was going to like prove that we could do something in Nina that is available to everyone for free, that'll make it easy and accurate to do. And it ended up working out. And so he's able to sell a lot of those devices. They're extremely useful. I own one. I still own that original one. And my images have gotten a lot better as a result of it, because I've really dialed in the tilt. So that's kind of it regarding Hocus Focus, though.
Eric?
Let me unmute myself and turn on my camera. That's great. Are there any more questions out there? Alex?
No. We're clear on questions. There's a few comments, pretty typical. I'm sure that George has heard it before. Apurva says, "Genius!" with an exclamation point. And oh, look at Philip. He says, "Can we talk a little bit on the noise reduction values in the advanced setting?" The noise reduction values in the advanced settings.
Sure. So let's go to what one of these images looks like. We zoom in. You all are no strangers to this, right? Our noises have dark current. They're generally noisy in the background, and we don't have the benefit of looking at stacked images when doing autofocuses. And so in order to determine if a star or a blob of pixels is actually a star, it is useful initially to sort of smooth the whole field out with the noise reduction to identify the structures. And that's where this noise reduction radius comes from. It's literally just a Gaussian convolution on the entire image. If you have a lot of noise, having this be a slightly bigger value can be useful. That's sort of one of the things that the basic mode controls there. That's one element. But then the other one comes based on the brightness of your stars and how to distinguish what's a star from the background by like it needing to be above the noise level, right? And so you can imagine being in a case where you have a high focal length scope, say f10, f20, your stars are going to be fairly dim. And if your background's also noisy, you're going to have a hard time telling a pixel being in a star or in the background. And so this is where the noise clipping and star clipping multipliers come in. There's a lot of nuance here involved, but ultimately there is some math that figures out what is the standard deviation of noise across the entire image. And then when I'm looking at a pixel, I need to be 2 times above the local background in order to determine I'm likely a part of a star. And that's where this 2 times 1 comes in.
So the first thing you do is you blur the image a little bit, right? That's your convolution.
Mm-hmm.
And can you just change the exposure to get a few more pixels, a few more photons in there?
You can, but your autofocus is going to take longer.
Yeah, that's a good question. How long does it take now?
So the right now, if so I have a 900 millimeter scope, f7 or so. It's a Tech 400, 140. And when I'm doing 3 nanometer hydrogen alpha, I'm not using filter offsets. I'm actually just doing it on the direct exposures.
Uh,
And I'm
Amen.
typically doing 3 to 5 second exposures. I'm consistently able to do an autofocus in under 40 seconds. And the reason I'm able to do that is because I've tuned my star detector to be able to pick up the stars within the field just barely enough so that I don't have to do long exposures, nor do I have to deal with filter offsets for like doing a focus with illuminance and then switching over to hydrogen alpha afterwards.
So what's your field? What is your chosen field of view when you do this?
Oh, good question. I typically do the entire frame because my tilt has been pretty well corrected. But if you wanted to adjust it, there's this options tab under autofocus. And these are the settings that are shared with the stock autofocuser too. So they're just in one place. You can crop the outside with this inner crop ratio. You can set it to like 0.8, 0.7. And when you do those autofocuses, or sorry, when you do the star detection and you turn on the annotation, you'll get a little box here in the middle. Actually, let's see if we can replicate that real quick. I don't use the setting often, but we should be able to get it. There it is. See, so it didn't do any detection outside of this box.
And where in the sky do you start? Where you're starting your imaging?
I like part of our philosophy with Nina, and I adopt this for Hocus Focus too, is to stop wasting time, right? And wasting time in my mind is slewing to a different part of the sky to autofocus and then moving, right? And so I do all of my focuses in the field I'm going to be imaging.
Your starting field. If a target is moving, starting out at 30 degrees and then getting higher and lower.
Yeah.
Where you're starting that target.
Well, I mean, so here's an when I set up my sequence to run, say like I kick it off 20 minutes after sunset. I'll do an autofocus at the very beginning and have it set to autofocus, say like every 40 minutes or every hour. And I'll just keep refocusing as the target moves to the sky without any additional slowing.
Yeah. Alex, there's a couple more questions you want to?
Yeah, we do. We do. We've got Linda wants to know if one isn't getting repeatable results from the Aberration Inspector, even though no setup changes have come in. How would you troubleshoot it, assuming the focuser is not the issue?
That is an issue. I'm still trying to get the routine to be more consistent. I have found that when you have a poor model fit, which is one of these parameters here, let me turn it on to show you where it is. Here, there's like this model R squared. So when this fit is worse, I've found most often that it's a problem with the quality of the star detection and the density of the field. Now, with aberration inspection, the tolerances are really brutal here because we're doing an autofocus routine on every star. We don't get to benefit from like averaging them together and reducing the error bars by depending on averages here. So I would say that if you're seeing a lot of variability, actually like save the autofocus run, load up the individual images here in the simulator camera, and just start like tuning your detector and making sure that you're getting every star in the field that you want to get, that they're fairly evenly spread out across the field, and that the quality of those detections are high.
Okay. Jimmy wants to know, and this is just about any focusing system, I guess. Why does he have to tell the focusing system what the step size is? It seems like something that the focusing program could calculate and decide what the best step is.
Oh, like having a wizard tell you what step size to use?
Yeah. I think that's what Jimmy's talking about.
Yeah, it's a question that comes up a lot. Honestly, it's just because it's one of those settings you set once and never touch again. The
Mhm.
motivation and incentive for me to implement that is pretty low.
Well, okay, let me say, how do you decide in the first place what that step should be
okay.
without Hocus Focus?
So what I recommend people do is do an autofocus run first and then see how many steps does it take to get from, say, like 2 to anywhere that's like 3 to 4 times that half flux radius. So at the ends, if you're going further out than 8 or 10, you've gone too far, right? And so just basically, I recommend having 3 to 4 points on either side of the minima. And that sort of informs, the distance from 8 to 10 to 2 at the bottom, divide that by 4, and then use that as your step size. And if you want an even faster focus and, have pretty good consistent results with your detection, then go for 3. Make your step size a little bit bigger.
Okay, that's your one piece of advice I give people is when you know what your good focus is, and if, let's say, it's like in that one graph you're showing now, it's just a little bit above 2, then make sure that your focuser goes out until that's 4 or 5 at least, and then decide that you're going to put 3 or 4 on each side and just divide what that takes.
That's exactly right. Yeah.
Yeah. Okay. And you only do it once, so why do we need to invent something to figure out how to do it? Is why it isn't in Hocus Focus. Does John wants to know if Hocus Focus has any advantage in lesser seeing conditions?
What I've seen is that Hocus Focus is a lot better at picking up dim stars than the other autofocus routines I've looked at. And the main one is like the one that existed in Nina beforehand, right? And so I found that if you tune this properly, even in poor seeing conditions, you'll be able to pick up those faint stars. And that's really tested at the boundaries of the autofocus curve anyways, right? Your stars are getting dimmer, they're getting more spread out anyways. So I find that if your detection works well at the boundaries, they're going to work well as in poor seeing conditions.
Okay. Isaac wants to know, how do you guys calculate the error bars?
So what you see here, this HFR and this median absolute deviation literally just comes from the points here. So we take the average of all these, in this case, that's the median, and then the deviation of all these points to that median is the size of the error bar. So we use that in here in the autofocus, right? This is what, about 5.8. This is maybe like 6.5. So you're looking at like a deviation of about 0.7 in that. It'll end up being just the number that's right here.
Okay, so the error bar is 1 standard deviation away from the mean, and the mean is the dot.
That's right.
Okay. And how do you and how does your program determine if a point is excluded from the autofocus curve and it's marked with the red X?
Yeah, there's this mathematical technique that I did some research on a while ago. I'm like drawing a blank on what it's called. The idea is that you can do the optimization to find the curve, and then you do it again while excluding individual points, and then you can do a statistical test of, is that points exclusion different enough from the original curve that had all of them to justify excluding it. And that's sort of one of the standard like statistical tests they do to find outliers. And so I incorporated that here as well. So, I mean, you can kind of see it visually that this one doesn't really fit the curve, and including it actually throws off the curve enough. So we can observe that here by actually turning off outlier rejections. And that goes from, was it 43.35 to I might have changed the settings too, so we'll see. Yeah, I changed the settings. These actually look a lot better, unless I loaded the wrong. Oh no, I loaded a different one. Sorry. This one I think is the one I used. Yeah, there you go. So I mean, this one caused a difference in 13 steps on the focuser by including it. So, so yeah, it's a statistical test of excluding a point having an impact on the curve itself.
Mm-hmm.
George, it's interesting, the tilt adjustment. If you have an SCT where that can be an issue, that's a real adventure getting those 3 knobs tightening. And if you have an RC, you know, you will be pulling the rest of your hair out trying to get that tilt right. So is there any help there in the tilt adjustment?
Well, I think the challenge we have when you have a secondary is that collimation could also be a problem, right?
Yeah,
and
true.
so you end up chasing these different things, like you change your tilt and then your collimation looks different, and you start going in this loop. And so the most frustrated people I see in the Nina Discord channels are owners of RCs. Because they have to deal with that problem. But if you're able to successfully dial in your collimation and then separately focus on your tilt, then there is hope, right? So you have, was it Skywave that made that product for helping to collimate your scopes? Other than the people that are using both of them, especially the automated solutions, they are successfully able to fix both their tilt and their collimation.
And with a refractor, it's not nearly the issue, unless your sensor just happens not to be parallel. Your little adapters are not parallel to the scope. You're not mucking around with the lenses at all.
That's right. That's right. So I mean, I own a refractor, and it is pretty straightforward to do it. Actually, speaking of straightforward, there is one complexity, even with refractors, that proves difficult. And let me show you what that is. It's when you see this left, right, top, bottom, like what's top and bottom on a telescope, right? Drivers sometimes flip images. Some scopes invert images too. The only real way to tell what's left, what's right, what's top, is down is to actually like test it out. And so one thing I've recommended people to do is to turn on a light in their observatory and put a piece of paper over part of the end of their scope and just sort of test out when I cover the top, you know, what part of my image gets adjusted. Because if it's the top half of what you see in Nina, then that's going to be what's represented as top here in the image. So even with refractors, it can be a little tricky. But, you know, I found that once you're able to successfully label, you know, what's top, bottom, left, right on your camera and your tilt adjuster, then it becomes a fairly iterative process thereafter.
The next set of questions we've got are not really questions. It's let's go back to the conversation we had that Jimmy started about why doesn't the program figure out what the step size is. Jimmy comes back and explains that he's got a number, he switches between a number of different telescopes. And unless Jimmy has lots of friends that loans him telescopes, we have to assume that he's got several telescopes. Anak explained to Jimmy, I think, that you really only need to set it once for any given telescope, camera size, and then all that other stuff, camera and things like that. And you can use a profile to do that. And once it's set, you just call up that profile for that particular telescope. Can you describe how one would do that in Nina, or such that Jimmy doesn't have to invent a new step size every time he swaps scopes?
Yeah, good question. So here in options, under general, there's this profile list here. you can click this and the this button right here to make a copy. And at that point, you can change and load your profile, assuming no. So like right now, actually, it's not letting me load one. It's because I have a connected device. But once all my devices are connected, it will let me switch. Now, I'm not going to switch. I'm running a custom build of Nina, and I know it crashes when I load a different profile. I'm working on something right now. So I'm not going to crash Nina right now. But if you were doing this, you would click load profile, and it would switch to a different set of settings. And what you'd end up modifying here is, where is it? We moved some of this stuff. Oh, under equipment here. So you have the focal length, you have focal ratio, and under the autofocus settings, which are here, is where you would put the step size. So generally, like you would want a profile per sort of optical setup you have. And then once you configure it, when you start up, you would pick the profile based on what device you're intending to connect. And you can switch profiles in the middle of a session too, as long as you disconnect your equipment and do that.
No, Nina has profiles. Isn't there a global profile which would populate your autofocus too?
There's only ever, so there is a default profile that everything sort of spawns off of, right? There are default settings for everything, but there is no place where if you update one setting, it updates in all profiles.
Well, what you would do is have two different profiles, one for one tube and another for the other tube. Everything else can stay the same. The mount's going to stay the same. The location's going to, whatever it is. And so by using profiles for each of your different combinations that you use, that's how you do it.
That's right. That's right.
Okay. Isaac is a fan of yours, and he's got some questions for you. In the AI, how do you convert between focuser steps and microns?
Ah, here it is. Under options, there is step size, which pulls it from your settings.
The profile.
Yeah, from the profile, or you can override it here just for the purposes of AI. Now, what this is doing here is it is using the offset in terms of focuser units as like the Z coordinate, you know, the up or down for the curve, and the microns are derived entirely from what is your step size of your focuser. So what that is saying is that since this one took 1,000 more steps to get into focus at the corner than it did on the other end, then it's going to infer the step size times the number of steps in terms of microns here. It's not like real, right? In terms of, I mean, these are like optical curves. So if you move it, say like say we thought that this was like 5 microns from bottom to top. If you change it 1 micron, you're going to get more than 1 micron of movement at the corners. So like we don't actually know that 5 microns here is how much you have to move the corner, because there's sort of like this quadratic effect from the base to the ends. So any sort of solution here should involve small adjustments and then seeing how you can get closer and closer to 0.
The next question Isaac's typed in is, what is the technical name test you're doing? Technical name test you're doing.
I'm not sure I understand the question.
Isaac, you want to put that one in again? And then back when he typed this in originally, you were talking a little bit about collimation. Can you make a collimation routine out of your Aberration Inspector?
Maybe, but honestly, I have not looked into it. I also don't own any telescopes that need to be collimated, so that's sort of the other problem there. But the Skyway folks have investigated the heck out of that problem space.
Okay.
I'm sure that there's a lot of different details associated with it than it is focus. But Isaac, maybe you'd like to see this. And this presentation, by the way, this is what I gave at NEAC about a year ago, and it's on Google Drive. Like, I'm happy to share a link to that. But this is the mathematical model used for that 3D curve.
And all the NEAC talks, if I understand correctly, are out in public now, right? You know about that?
I don't know, actually.
I think I got a notice to that effect, and I may be starting a rumor here that I shouldn't be starting. So let's go back to Isaac. Can you give us the name of the outlier test for excluding autofocus points?
I can. I would have to look in my code because I'm pretty sure I put it in my code. How about while we talk, I pull it up, and if I find it in time, I'll share it.
Okay.
Well, that's about the end of the questions in any case, isn't it? Oh,
Well, Philip popped in with one.
Philip.
Well, his comment. Thanks for all the great work. Really impressive. And Linda, I guess, was at NEAC and said that the presentation was very good.
Oh, thank you. So I tried pulling up my source code and loaded up a lot of wrong windows. So I'll find it and maybe post after the fact on the YouTube channel what it was.
Okay. If you go to the YouTube channel, you can just make comments, Isaac, ask that particular question, and George can see it and answer it. Okay.
I think you can stop sharing, George, if you like.
All right.
Isaac, what are your thoughts about offset versus using actual filters? I can tell you my experience, actual filters work better. Offsets are simpler once you do the offsets. Do you have other thoughts about that, George?
I have gone back and forth on this. I have found that the just temperature variations, even within your scope and your wherever your environment is situated, that you have enough dispersion between running it initially and running it the next time, between filter A and filter B, that I don't have confidence in that number, right, being particularly accurate. I found that it can vary from, like, say, 70 steps to 120 steps, right? I'm just, made up some numbers, but I did see a big enough dispersion in my cases. And frankly, like, for me, focus runs fast enough that it's not worth, like, I spent all this time trying to get a very precise focus. Why then throw an imprecise number into the mix?
I think that's the
I've actually given up
thing.
on use of offsets.
If it were a 10-minute delay or something, you wasted imaging time, we might think about it, but for a minute?
Mm-hmm. Okay. Yeah. I just got a general question. Let's say I'm using the regular autofocus that comes with, that Nina comes with, and I switch to your autofocus program. How much, practically speaking, does one change from the other? How much does the focus position change?
Frankly, I haven't done that analysis. What I have found is that it's a faster routine, and that the HFRs from the images produced by it tend to be lower. And that's sort of the feedback that's been shared with me.
Well, that's
yeah.
Okay, so it goes faster and your stars are smaller.
Yeah.
Yeah, I think that is the ultimate test. And we're always looking to get better focus and tighter stars. So
yeah, and I mean, just a bit of commentary on, like, Nina as a system. It's sort of baked into the philosophy for how it was built. It's like to never serialize operations when they can be done at the same time, right? And so, like, for example, if you're doing an imaging session in Nina and like you finish the image capture, it's going to start the next exposure while it's writing to disk, while it's doing, like, pre-processing on it. And so you'll see that you're able to take more images in a night because Nina does that. And this autofocus routine does exactly that as well. So it does an exposure, it moves, it does an exposure, and in the meanwhile, in the background, it's doing its analysis. So it's not And that's
You
one of the
probably
reasons-
have more insight on that. You have any idea how many Nina users there are out there?
last I checked, at least 10,000 in terms of like download counts, and like when an update goes out, you see how many downloads happen, and it's measured in like the 5 digits at least, I believe.
Why isn't Hocus Focus, Isaac wants to know, why isn't Hocus Focus the standard focusing procedure in Nina?
Ah, another good question. That's on purpose. The reason is I can make updates to Hocus Focus without asking Stefan to roll it out for me. And so we don't need a major upgrade in the Nina core library, which is a scary thing for some people to change, right? You know, if it works, why break it? So I can update Hocus Focus independently of Nina itself. And that's the main reason why it's separate.
Isn't that the way most of the add-ins work in
It's
Nina?
the way all the add-ins work.
Yeah.
That's
So anyone can have an update and break the system, so to speak?
generally, no. I mean, yes, technically a plugin could break Nina, but the idea there is if you're not using the functionality, don't install the plugin.
Okay.
Yeah.
Are
we doing? Are we
counting on the community to like do good releases and test their stuff before things go out? But you know, I do a lot of testing on Hocus Focus before I release updates. And I'm gonna like just go into this plugin page so you can see, right? There's a long list of plugins available here. This is a very active community. And when we tell people, hey, please jump into the Nina Discord to report bugs, the reason is because all the people that are developing this are there, right? You see an issue, you have a feature request, whatever, you put it in there, and you'll get someone that is familiar with it answering your questions. And sometimes you'll get a bug fix 30 minutes later.
You know, Nina has I mean, I remember a couple of years ago, it was just kind of on the periphery of software use, and now it seems to be the go-to software, and it's free.
Yeah. Isaac wants to know.
He's still asking questions.
He's still asking questions. Isaac wants to. Isaac,
Happy to answer them.
does the rule of having a max HFR of 8 to 10 still hold for larger scopes?
I mean, generally, I mean, say you had like a 2000 millimeter scope. The smallest stars you have are not going to be 2 pixels. They're going to be bigger, right? And so I say aim for 3 to 4 times whatever your minimum is.
Okay. Okay, we're finished temporarily. Let's see.
We're finished
Turn it
temporarily.
back to Eric.
Oh, that was a great presentation, George. Even though I don't use Nina, I am fascinated. And you held a very good audience. I suspect if you look on YouTube, in a week or so, you'll find you have a couple thousand people have viewed this video.
You hit a high of 85 during the presentation, right at 6:59, and then something fascinating started on television, and it dropped, but it came back.
So I think we're good. I don't know if we have any more announcements, but for all of those in the U.S., you know what tomorrow is, and you know what your responsibilities are if you haven't already done it. So please go out and vote for your candidate of choice.
And we really should end it there, except that we got more questions.
Isaac again.
Well, no, Bob's here too, and Terry. Oh, Terry's just complimenting. Anyway, where does that 3 to 4 times value come from? That on 8 to 10, HFR for your maximum readings on the outside of the wings of the parabola.
So that just sort of comes from doing this enough times, right? When you're very, very zoomed in at the bottom of a focus curve, it's almost a parabola, right? And so if you're doing very, very small movements, you'd actually want to fit a parabola instead of a hyperbola. What I found is that any amount of error in your imaging or your detector gets thrown off a lot by those very small movements. So I found that if you stretch it out a bit, that you end up getting more consistent results. I found that if you go out further than 3 or 4, it's overkill. And if like you go just between, 0 and 1, you get a lot of volatility in terms of your measurements. And so that's sort of where, that 3 to 4 heuristic came from. It's not particularly scientific, but I've seen it enough times that I think if someone did a test, that they would prove that out.
Okay. Bob Bryant is asking how you determine the microns per step size, and he specifies a Red Cat 71 belt focus, and I don't know if that requires anything special from the usual way of doing it. But how do you figure out how many microns there are in a step size? Or, yeah.
Well, so I have a night crawler, and it's fortunately like published, right? That number is easily accessed on the website for the device. But if it's not, what I found is that your focus or draw to, you could move it out 10,000 steps and then literally just measure the length of your focus or draw to.
Digital micrometer works really well, and you only have to do it once.
You only have to do it once. That's
only
right.
have to do it once. You don't have to do it electronically or run any program.
Yeah. Now, there are some camera lenses that shift internally, and you can't do that. But it might not be necessary to worry too much about it. What you want to be able to do is how many steps do you have to take between what it reports as perfect focus and what it reports as 5 or 6 times, or 3 to 4 times that. And once you know that, then that you can call it as you see. And you may not ever know the precise number of microns, but what you need to know is how many steps you have to take to get enough samples to generate the curve.
Digital micrometer.
And if you can get into it, there are
the focusers for my refractors that I use, you just put a digital micrometer and one time you have it. I think we're at the end of our presentation. We agree? Are we ready to say goodnight?
Well, there are more questions coming in, but they can be answered over the over YouTube also.
They can be answered on Discord too, right? You have a Discord channel, so post a question on Discord, and I'm sure you'll get back to them.
Yeah, and I mean, you can also ask on the YouTube. I'll hop on there afterwards and answer some questions there. I know some people really don't like Discord. I don't understand it, but some people really don't like it, and so I'll hop onto the YouTube page too and answer questions.
And after the program, we usually stay on a little bit. You're welcome to stay with us.
Okay.
If you like. But I think we're at the end of our program. So good night, everyone, or good morning, depending on where you are. And again, vote tomorrow if you haven't already and you live in the United States. And if you don't live in the United States, please don't vote.
Good night.
Good night. Good night,
Take care.
everyone. See you next week.